Hey students, guess what time it is? It's science time. Get out your notes and let's start learning. So let's say you want to find out the weight of a hydrogen atom. Where would you go to? You would look at the periodic table. If you want to find out the weight of an oxygen atom, where would you go to? You go to a periodic table. So now let's say you want to find out the weight of carbon dioxide. Where would you go to? Well, if you look at the periodic table, you cannot find carbon dioxide on there. Or if you want to find out the weight of potassium chlorate. If you look in a periodic table, you cannot find potassium chlorate. So instead, this is something that you're going to be doing a lot of in order to find out the weight of a molecule. And so this is what's referred to as a formula mass. So the formula mass may also be called by several other names. Sometimes it's called a formula weight and is abbreviated as FW. Sometimes you'll hear it called a molecular weight, which is sometimes abbreviated as MW. Sometimes you'll hear it called a molecular mass, and sometimes it may go by other names here. But typically, whenever you're looking at this, if you ever hear the word something either formula, molecular, or even sometimes atomic, and either followed by the word weight or mass, what you're doing is you're finding out the weight of an atom or of a molecule. Now, personally, I tend to call it a formula weight most often. And sometimes you'll see me abbreviate it with FW quite often. So, it is the sum of the atomic masses of all the atoms represented in the formula. In other words, it's all the weight of each individual part within the molecule. So the way that you go about figuring this out is you write the number of moles of each element in the molecule, assuming that you have 1 mole of that compound. And we'll talk a little bit more about that later on. Second, you calculate the number of grams of each element by using the number of grams per moles, which is the atomic weight of each element. You find that on the periodic table. And third, you add all the masses together to get the weight of the formula. So let me give you examples, and then we'll come back to this. So trying to find a weight of a compound is similar to trying to find the weight of a car. So let's use a little bit of imagination, and let's pretend this is an actual car. So I'm just using this as an example of a way to illustrate an idea. Now, if you had to weigh an actual car, but the only thing you had to weigh it with was a set of bathroom scales. Now, the problem is bathroom scales can only go up to maybe 300 or 400 pounds. A car weighs a lot more than 300 or 400 pounds. How would you go about finding out the weight of a car using only a set of bathroom scales? So, if time and effort was not an issue, what you could possibly do is you could take the car apart and weigh all the individual parts. And by weighing all the individual parts, then if you were to add everything up, you then could figure out what is the mass of the car. So using this little very simple Lego car here, we're going to go ahead and do that. So just to verify, this car has a mass of 16.19 grams. So my car is 16.19 grams. Okay. Now, if we get something close to 16.19 grams, hopefully this will help illustrate the idea. So let's see how close do we get to this value here. Now this is not the best set of scales here, but for this type of situation it should work okay. So we'll have to take the car apart, and as you can see here, we have a body, and the mass of the body of the car. So the body has a mass of, I think it's about 4.36 grams. The numbers fluctuate a little bit, and that's okay. So I'm using B for body. We also have two axles. Now, if I weigh an axle has a mass of about 1.73 grams. 73, 74, somewhere around there. Now, just to kind of illustrate a point, do I have to weigh each individual part individually? And if you notice, basically I get the same number here. This one says 1.74, the other one 1.73, kind of fluctuates a little bit. That's fine here. So really I only have to just measure one of those. Then also I have 4 wheels. And a wheel has a mass of about, well, looks like it's about 2.07 grams. Okay, and again, if you look at the mass of each wheel, 2.06, 2.07, 2.08, 2.07, somewhere around there. So they're all roughly about 2.07 grams. Okay, so really, and especially if I have multiple parts, all I really have to do is just weigh one of them and then multiply it by however many I actually have, just as a means of saving time. So let's take this one step further. So we have our masses of each individual part, and then we have the mass of the entire car. And let's see how close do we get to this value here. So let's go ahead and figure out how much does this car weigh based upon the individual parts that makes up the car. So one body has a mass of 4.36 grams. One axle has a mass of 1.73 grams. One wheel has a mass of 2.07 grams. Okay, so I have one body, one axle, one wheel. And even though we call this a car, let me flip this over so you can see all the parts to it. Technically, car is its common name. The scientific name for this car is going to be BA2W4. Now, why am I calling that? That's because it's made up of one body, which is what we see here, where it's made up of 2 axles. So A is axle. I got 2 of those over here, and W4 because I have 4 wheels. Okay, so what we're going to do is we're going to turn this into a formula and find out what is the weight of a car based upon this formula here. Alright, so if I have one car, so one car is made up of all these parts here. It's the actual car. I have one body. Now, one body is equal to 4.36 grams. This becomes my conversion unit. So what I'm going to do is open up a set of parentheses, and I'm going to put, in order for the body to cancel out and leave me with the mass, I want to put 4.36 grams on top and one body on the bottom. This way the body will cancel out, and you get a mass of 4.36 grams for the body. Now, you might be thinking, it's like, well, wait, this is really easy to do. Yes, this is very easy to do. But please set this up this way, because when we start getting into formula weights and eventually into empirical formulas and percent of an element or percent of the compound, you're going to have to set it up this way. So there's kind of a method to my madness here as to why I want you to do things in a very specific sort of way. So set it up exactly how I'm showing it to you here, where all we're doing is just getting some practice for what you're going to be doing later on. All right, now if you look at the formula here, so one car is made up of two axles. So what I'm going to do is put down two axles, open up another set of parentheses, and go over here, and one axle is 1.73 grams. So I'm going to put 1.73 grams on top, and one axle on the bottom. This way, axles will cancel out. So now, we multiply it out. I'm going to take 1.73 times 2, and I get 3.46 grams. Of axles. And what that tells me is all the axles added together will have a mass of 3.46 grams. And then the last part, the car is made up of 4 wheels. So I'm going to put 4 wheels over here. Open up a set of parentheses. One wheel is 2.07 grams. So I'm going to put 2.07 grams on top, and then one wheel on the bottom. This way wheels will cancel out. So now I'm going to take 4 times 2.07, and we get 8.28 grams. For wheels. Okay. That means if I were to weigh all the wheels, assuming they're each one is pretty close to being the same here, I should have a total mass of 8.28 grams just for the wheels. The car will be made up of 3.46 grams of axles and 4.36 grams of the body. So all we're doing is we're finding out the weight of all the individual component parts and kind of all the subgroups of those individual parts. And now, to find out the weight of this whole thing, we want to add all these values together. So, if I take 8.28, or add that in the calculator, plus 3.46, plus 4.36. And kind of interesting set of numbers here. And I get a mass of 16.1 grams is equal to BA2 W4. Now, if you look at my value here versus what I have over here, it's pretty close to it. Okay, and again, these are not really the best scales I'm using here, so I was expecting, actually I kind of expecting a little bit more of an error. So I'm off by almost 1 gram, so 0.09 grams. So that's pretty good here. So it's possible to find out what is the weight of really any object if you were to take that object, break it down into its individual parts, and then if you weigh all those individual parts, and especially if you have groups of those things, of those individual parts here, you can kind of speed up the process by just taking the weight of one of those and then find out what is the mass of those, kind of the subgroup. And then once you have all the masses of all the individual subgroups, add them all together to get the mass of the whole object itself. So when you're finding the formula weight, basically that's what we're doing. So let's take another look at a different example. Now with the example with the car, that's just a single object, and you can find the weight of a single object here. It's made up of several different parts. But we can also do the same thing with a group. And if you remember, earlier on when we ended up doing this activity, when we weighed out these different items, and then we also weighed out like a dozen, in this case, paper clips, and then we end up using all the objects, and from that find out how many of those objects we had versus your calculated. So we compare the actual versus the calculated, you find out these two things are pretty should be pretty close to each other here. But one of the items, and on the back side of the paper, was this one.
And probably the reason why I have this unusual one here, which I called BIP3. And if you remember, B stands for binder clips, I stands for index cards, and P3 meant it had 3 paper clips. And so this was kind of like my molecule. And the way that this one worked out, it still worked out to be very similar to here, though I don't have the work being shown. But one thing that you did here, or actually I did, was I took 1 dozen of the BIP3s, put them on the scale, and got a mass of 112.28 grams for 1 dozen. Now, we could have figured out this number here based upon the masses of all these individual parts. So let's go ahead and do that now. So this is going to be like our molecule. And these are kind of like our atoms. So we're going to find out the weight of this molecule by using these atoms here. Alright, so let me transfer some of the numbers. So the formula is BIP3. So binder clips, 1 dozen of the binder clips was 34.41 grams. So I'm going to write this number down here. So 1 dozen binder clips is 34.41 grams. Alright, for index cards, 1 dozen index cards is 30.86 grams. So 1 dozen index cards is 30.86 grams. For the paper clips, 1 dozen paper clips was 15.67 grams. Okay, so again, for each one of these items, we weighed out a dozen of those, and from those dozen, we found out what is the total mass of that 1 dozen. So now, let's do something similar to what we did before. So here's the formula. And we had 1 dozen of these objects here. So if I had a dozen BIP3, how many would I have of just the binder clips? Well, if I have a dozen of these, I'm going to have 1 dozen binder clips. So I'm going to put down 1 dozen binder clips. If I have 1 dozen BIP3, how many index cards would I have? I would have 1 dozen index cards. If I had 1 dozen BIP3, and every one of those index cards had 3 paper clips attached to it, and in fact I had 1 dozen of those, that would mean I would have 36 paper clips on there, or 3 dozen paper clips. So this, we're going to use this information here and the mass of each dozen over here to find out the weight of the whole thing. So 1 dozen binder clips, with opposite of parentheses. I have 1 dozen binder clips is equal to 34.41 grams. So which would I have to put? Do I put dozen over grams or grams over dozen? If I put dozen over grams, if you remember, technically this whole thing is over 1. So dozen is on top. In order to cancel it out, I need dozen on the bottom. Otherwise, I end up with if I put dozen on top, I end up with a dozen times dozen would give me a dozen squared. Grams on the bottom would be dozen squared per gram. There's no such units. So I need grams on top. So I have 34.41 grams all over 1 dozen. Dozens will cancel out. So 1 times 34.41 gives me 34.41 grams of binder clips. Let's do the same thing with index cards. So 1 dozen index cards is 30.86 grams. So this is dozen. Technically this is over 1. So I need dozen on the bottom. So 1 dozen index cards on the bottom and 30.86 grams on top. Dozens will cancel out, which now gives me 30.86 grams of index cards. And the last one for paper clips. So I have dozen, technically, again, is over 1. So I need dozen on the bottom over here. So 1 dozen paper clips is 15.67 grams. So 1 dozen on the bottom, 15.67 on top. Dozens will cancel. So this time I'm going to have to take 3 times 15.67. So 3 times 15.67 grams. And I get 47.01 grams of paper clips. So for BIP3, these are kind of the subgroups here. I would have a total mass of 34.41 grams of binder clips, 30.86 grams of index cards, and 47.01 grams of paper clips. Now to find the mass of the whole thing, we need to add all these values together. So if I have 47.01 plus 30.86 plus 34.41, and I get a mass of 112.28 grams is equal to 1 dozen BIP3. This is my answer here. This is the formula weight for this molecule, I guess you can say here. So how close were we? Wow, look at this. I was expecting this. When we weighed this out, it was 112.28 grams. What we just calculated, we got 112.28 grams. They're exactly the same. So, again, this is a way of finding out the weight of basically of a compound by knowing the weight of all the individual parts that makes up that compound. Now, the reason why I have it written out this way is because later on we're going to be using this for an additional calculation. When we start getting into how many moles and how many molecules, this is going to become another conversion unit. So this is just one stepping stone for something else that we're going to be doing for later on, which is going to be leading on to another step later on. So what we just did here is we took the formula BIP3 and assumed we had 1 dozen of BIP3. So that would mean, and then find out the weight of all the individual parts of all the binder clips, all the index cards, all the paper clips, for a dozen each of each one of those groups here. And then with BIP3, that means I have 1 dozen binder clips, 1 dozen index cards, and 3 dozen paper clips. And by multiplying by the mass of each one of those, we can find out what is the mass of binder clips, what is the total mass of index cards, and what is the total mass of just the paper clips. And by taking all the individual masses of all the groups within the compound, then find out what is the mass of the whole thing. So again, this is kind of like a compound. But where do we find this information? And that is, the place is here. Now you probably can't see it too well here, but when we're looking at a compound is made up of 2 or more atoms bonded together. And to find out the weight of a compound is, if you look on the bottom portion, these are, the masses down here are grams per 1 mole, which is the same thing as a gram per 1 dozen. So these are like the mass of all the individual parts, the same way that these are the masses of all the individual parts. And so by knowing the mass of all the individual parts of the atoms, if we're dealing with a compound, we can then use this information here to find out what is the weight of a whole molecule. So if you want to find out the weight of a sodium chloride, we would have to look at how much does sodium weigh and how much does chlorine weigh. If you want to look at baking soda, which is sodium, hydrogen, carbon, and oxygen, we have to take a look at each one of those individual parts and add up all those masses together. So the numbers down here on the bottom are the same thing as these right here, which ultimately we're going to be doing this exact same thing as this. Okay, so again, when you're writing these things out, write them out in a very specific sort of way. So now I think we're ready to go ahead and start working on some compounds.
Now, if you look at this, we have potassium chlorate. The formula for potassium chlorate is 1 potassium, 1 chlorine, and 3 oxygens. Potassium has a positive 1. Chlorate is one of your pi-atomic ions. It has a negative 1, so positive 1 and a negative 1 makes it neutral. So if you look at the way the potassium chlorate is put together, it is made of 1 potassium, which is attached to a central chlorine atom. And the central chlorine atom is also attached to 3 oxygen atoms. So here's your potassium, and your ClO3 is your 1 chlorine and your 3 oxygens. Now, looking back at the formula, if you notice with the subscripts, we have a 1, and a 3. And again, you remember, you don't write 1s down. So you have 1 potassium, 1 chlorine, 3 oxygens. So if you look at this molecule, you'll see 1 potassium, 1 chlorine, and 3 oxygens. But then, if you look at this whole page here, and if you count them out, I have a total of 12. I have 4 by 3, so I have a total of 12 potassium chlorates. So, how many potassiums would I have? So if I have 12 potassium chlorates, I'm going to have, as you can see here, I have a total of 12 potassiums. If I have 12 potassium chlorates, I'm going to have 12 chlorines. And then since each potassium chlorate has 3 oxygens on it, and I have 1 dozen of those, if you count all of these oxygens out, I have a total of 36 oxygens, which is the same as 3 dozen. So I'm going to have 1 dozen potassiums, I'm going to have 1 dozen chlorines, and I'm going to have a total of 3 dozen oxygens. Because I have 36 oxygens, that's 3 dozen. So the main thing to take away from this is that if I have a 1 to 1 to 3, that could be representing a single molecule of potassium chlorate, or it can also be representing a whole group of potassium chlorates. So this could be 1 atom, 3 atoms, or 1 dozen, 3 dozens. And that's going to be a very important concept to understand here. And even if I go something like this, again, I have potassium chlorate, so I have 1 to 1 to 3. And if you count all the potassium chlorates I have on here, I have a total of 13. And if you're familiar with this term here, 13 is sometimes called a baker's dozen. So if I have a baker's dozen of potassium chlorates, I'm going to have 13 potassiums. If you count them here, I have 13. I'm going to have 13 chlorines. And since each potassium chlorate has 3 oxygens, and I have 13 of those, that's 39 total oxygens. Or if I put that into baker's dozen, that's 3 baker's dozen. So I have one baker's dozen of potassium, 1 baker's dozen of chlorine, and 3 baker's dozen of oxygen. So when I'm dealing with a group, my proportions still remain as 1 to 1 to 3. Now, if you look at this next slide, again, we're looking at potassium chlorates. And I'm just kind of abbreviating here. So if I have a single molecule, I'm going to have 1 atom of potassium, 1 atom of chlorine, and 3 atoms of oxygen. If I have a group of them, if I have a dozen, that means I'm going to have 12 atoms of potassium, 12 atoms of chlorine, and 36 atoms of oxygen, which, if I convert it to dozen, that's 1 dozen potassium, 1 dozen chlorine, 3 dozen oxygen. If I have a baker's dozen, I have 13 atoms of potassium, 13 atoms of chlorine, and 39 atoms of oxygen. And that's 1 baker's dozen of potassium, 1 baker's dozen of chlorine, and 3 baker dozens of oxygen. Now, this next part is one where it's the same train of thought, but sometimes people kind of get hung up on this a little bit. It is a mole. A mole is a counting unit, no different than a dozen, or no different than a baker's dozen. And 1 mole is equal to 6.022 times 10 to the 23rd, just like 1 dozen is 12. So if I have 12 of anything, I have 1 dozen. If I have 13 of anything, I have 1 baker's dozen. If I have 6.022 times 10 to the 23rd of anything, I have 1 mole. So if I have 1 mole of potassium chlorate, I'm going to have 6.022 times 10 to the 23rd atoms of potassium, 6.022 times 10 to the 23rd atoms of chlorine, and 18.066 times 10 to the 23rd atoms of oxygen. Now, technically, this is not how you write out a scientific notation. So the more appropriate way is this way here, but I'm going to go back up to this one here. If you look at this number, you'll see that this number is 3 times bigger than this value over here, which means if I have 18.066 times 10 to the 23rd, I have 3 moles. No different than 36 atoms of oxygen is 3 dozen, or 39 atoms of oxygen is 3 baker's dozen. 18.066 times 10 to the 23rd atoms of oxygen is 3 moles. And the key thing to take away from this is that if you notice for all these, whether you're dealing with a single or groups, the proportions are always going to be the same. 1 to 1 to 3. And that's basically what we're looking at here, is that when we're looking at this, this is not just a single molecule of potassium chloride. This can also be representing a group of atoms within a molecule. So let's take this one step further here and work out some example problems.
Now, before we get started, one thing I want you to be aware of when you're looking at the periodic table and you're looking at the numbers down here in the bottom. Okay, so let's take oxygen as an example. So when you're looking at oxygen, you'll see the atomic number up on top, which is the number of protons. So right now, we're not going to be worried about those here for quite some time. You have the symbol, you have the name, then you have this number down here. And this is what we're going to be concerned about. Okay. Now, like for oxygen, you'll see 15.9994. Okay. Now, depending upon which version of the periodic table do you look at, you might see the number a little bit different. For example, if you look at this type of periodic table that I gave to you at the beginning of the year, you'll see that number down here. If you're using something like the Ashland University periodic table, the number might be a little bit different. Don't worry about that. Just stick to one periodic table. The answers may vary a little bit, but that's okay. Okay, there's going to be a little bit of discrepancy among the different periodic tables here, but they should all be roughly about the same. So when you're looking at this number here, this is what's based upon 1 mole of oxygen. In other words, if you count 6.022 times 10 to the 23rd atoms of oxygen, it would have a mass of 15.9994 grams. So this unit down here is a unit of a gram per mole. And that's the unit for this value here, which means that when you put one value over the other one here, this dividing line here is kind of like an equal sign. That means it's 15.9994 grams is equal to 1 mole of oxygen. And because this is an equality, that means within the parentheses, if you remember, you can put one value over the other one. So in other words, you're going to have 15.9994 grams over 1 mole, or it can also be set up as 1 mole over 15.9994 grams. So this is going to become a conversion unit. So we can either put grams over mole or mole over grams. Okay, so that's going to be important for a lot of the stuff that we're going to be doing throughout the rest of the remainder of the year. So this number down here, that is basically the same thing as this right here. So you have 15.994 grams is equal to 1 mole of oxygen. That's kind of like saying this right here, 1 dozen binder clips is 34.41 grams. So this number here is kind of like this number here, okay, for each one of these. So here you had to weigh out a dozen of those objects. Here, a mole of those objects were weighed out for you to find out how many grams were they. And just like, because of this equality, you can put one value over the other one, which was done over here. Okay, so let's go ahead and work on the answer for potassium chlorides.
All right, so since we were just talking about the potassium chloride, find the formula mass of potassium chloride.
All right, potassium chloride. Starting off with the formula. Potassium is K, positive 1. Chlorate is one of your polyatomic ions, ClO3, negative 1. So you have positive 1, negative 1, charges balances out. So this is your formula for potassium chloride. So if you were to have 1 mole of potassium chloride, how many moles of potassium would you have? This is just like me saying if you had 1 dozen potassium chloride, how many dozen potassiums would you have? So in this case, you would have 1 mole of potassium. And again, how many moles of chlorine would I have? And this would be similar to if I were to have 1 dozen potassium chlorate, I would have 1 dozen of the chlorines. Well, in this case, I would have 1 mole of the chlorines. And if I have 1 mole of potassium chlorate, and every potassium chlorate were to have 3 oxygens, I'm going to have 3 moles of oxygen. And this is very similar to what we did right here with the BIP3. If you had the formula, if you had a dozen of those, that's how many 1 dozen BIP3 will give you 1 dozen binder clips, 1 dozen index cards, 3 dozen paper clips. Now, we need this information here. And where you find that is here. Okay, so we were able to weigh these. In this situation, we wanted to look these numbers up on the periodic table. Alright, so potassium. If you find potassium on the periodic table, we're going to up a set of parentheses. I'm going to use this as kind of as a visual aid as to what we did last time. So potassium has a mass of 39.098 grams. That's for every 1 mole. Okay, so we're going to put down 39.098 grams all over 1 mole. Okay, and just kind of like with the oxygen here, the number that we see down here, is an equality. So you can either put grams over mole or mole over grams. So that would be how many grams of potassium we would have. So if I take 1 mole of potassium times 39.098 grams, moles will cancel, and that will give me 39.098 grams of potassium. Same thing for chlorine. If you look on the periodic table, chlorine is towards the right hand side. So 1 mole of chlorine is 35.453 grams. Moles are going to cancel, and we'll have 35.453 grams of chlorine. And then for oxygen, now as you can see for oxygen, it looks something like this. You'll see 15.994 grams. So I have to use one of these two over here. So since moles is down here, already down here on top, moles is on top, I need moles on the bottom, so I need to use this conversion here. It's 1 mole on the bottom and 15.9994 grams. Moles are going to cancel. So if I take 3 times 15.9994, I end up getting 47.9982 grams of oxygen. Okay, so that's kind of similar to what we did with the BIP3. We took the number dozen for each one of the component parts, multiplied by how much was a dozen of each one of those items, and then to find out the weight of the whole thing, we had to add everything together. So that's the same thing that we have to do here. So when I add up all these values together, I get 122.5492. Typically, if you take it about 3 places past the decimal points, you should be fine. Now, one thing I want you to do is when you get your answer, also put down it's equal to 1 mole of potassium chloride, KClO3. This is your answer. Now later on, this is going to become another step. So this is going to become another conversion unit for some later stuff down the line. Okay? If you have any questions on that one, let me know. Let's move on to the next one.
What is the molar mass of barium nitrates?
All right, the next one is barium nitrate. Now what I'm going to do is get you started on this one, and then I want you to work it out and then give me the answer. Now barium nitrate, barium is Ba positive 2. Nitrate is 1 pair of proatomic ions, NO3 negative 1. Positive 2, negative 1, therefore you need 2 nitrates. So I'm going to close it up in parentheses. And this is one reason why we went over ions, because if you mess up on the name of this, if you mess up on the formula, it's going to throw everything else off in the process. So if I have 1 mole of barium nitrate, let me try to draw this out here. So barium nitrate kind of looks like this. You have a barium, it's attached to 2 nitrogens, and each one of those nitrogens has 3 oxygens attached to it. Kind of looks like this. Okay, so here's my barium with a positive 2, and I have a nitrate, negative 1, and this one also has a negative 1. So here's my NO3, and here's my other NO3. So I have 2 groups of NO3. Now, if I were to have a dozen of these, I would have 1 dozen bariums, I would have 2 dozen nitrogens, and I would have a total of 6 dozen oxygens. Now, if I have a mole of barium nitrate, I'm going to have 1 mole of barium. So I'm going to write that down here. I have 1 mole of barium. If you have to distribute, I want to have 2 moles of nitrogen. And then 2 times 3, I'm going to have 6 moles of oxygen. Okay, as you can see here, so for 1 barium nitrate, there's 1 barium, 2 nitrogens, and 6 oxygens. That's what we have over here. So what I want you to do is go ahead and tell me what is the formula weight for this compound. Select your answer, and then we'll work through it. Alright, so now, hopefully you did well on that one. So barium, if you look in the periodic table, barium is in group 2, and that has a mass of 137.9 0.33 grams for every 1 mole. Nitrogen has a mass of 14.007 grams for every 1 mole. Oxygen is going to be 15.9994 grams for every 1 mole. Alright, so now let's work these through. So moles will cancel out. So 1 times 137.33 is 137.33 grams of barium. Nitrogen, 2 times 14.007 is 28.014 grams of nitrogen. And 6 times 15.994, I'm sorry, 999,394 is 95.9964 grams of oxygen. So we just found out what is the total weight of barium, total weight of nitrogen, and total weight of oxygen. I'm going to add up all the results together, and you should have 261.3404 grams. Is equal to 1 mole of barium nitrate. I ran out of room there. Again, this is going to be a conversion unit for later on.
What is the formula weight of sulfuric acid?
If you have sulfuric acid, hydrogen is +1, sulfate is -2. So +1, -2, I need 2 hydrogens to balance it out. Now if I have 1 mole of sulfuric acid, so for 1 mole of this whole thing, I'm going to have 2 moles of hydrogen. So I'm going to write down 2 moles of hydrogen. 1 mole of sulfuric acid, I'm going to have 1 mole of sulfur. Put down 1 mole of sulfur. 1 mole of sulfuric acid, I'm going to have 4 moles of oxygen. Okay, so go ahead and work this one out. Now, hopefully you did well. So let's go ahead and get the answer for this one. So hydrogen is 1.0079 grams for every 1 mole. Again, depending upon the periodic table, this number may vary just slightly here, but just go ahead and use whatever you have. Sulfur is 32.066 grams for every 1 mole. Oxygen is 15.9994 grams for every 1 mole. So moles will cancel. Let's go ahead and multiply them out. 2 times 1.0079 comes out to be 2.0158 grams of hydrogen. Sulfur will be 32.066 grams of sulfur. Oxygen is going to be 63.9976 grams of oxygen. So find the weight of the whole thing. You have to add up the numbers, which comes out to be 98.0794 grams. It's equal to 1 mole H2SO4. So again, this is going to become another conversion unit.
What is the formula mass of phosphate? Now this is an ion.
Next one is phosphate. Now phosphate is applied to ion, which is PO4 -3. Now some people will think, oh geez, what do you do? It has a -3 charge up here. So let me show you what you do. Is first of all, you assume you have 1 mole of phosphate, which means you're going to have 1 mole of phosphorus, and you're going to have 4 moles of oxygen. Now, this charge up here, -3, does not matter. Even though there's 3 extra electrons on here. If you remember from a while back, electrons have such small mass that in comparison to the weight of the atoms, they're rather insignificant. It'll be like worrying about a dust particle landing on a blue whale. And will a single dust particle greatly contribute to the mass of the entire blue whale? Not really. So, same thing with this, is that the mass of electron is so insignificant into the mass of this, it does not matter. So just ignore the charge. So go ahead and work this one out. So if you have 1 mole of phosphate, what is the formula weight for phosphate? PO4 -3. Alright, so hopefully you did well. Let's go and work this one out. So if you look in the periodic table, phosphorus has a mass of 30.974 grams for every 1 mole. And if you look at on the periodic table, oxygen is 15.9994 grams for every 1 mole. Eventually you'll be doing this so often you'll get to the point where some of these numbers you'll start memorizing. Alright, so for phosphorus, moles will cancel out. You're going to have 30.974 grams of phosphorus. For oxygen, you're going to have 63.9976 grams of oxygen. So the total mass will be 94.9716 grams is equal to 1 mole PO4 -3.
Number 5. What is the molar mass of magnesium sulfate?
Now the next one is kind of a two-part one here, and you'll see why here up to bit. So we're going to find out what is the molecular weight or formula weight for magnesium sulfate. Now magnesium is Mg+2. Sulfate is one of your polyatomic ions, which is SO4 -2. So you have +2, -2, charges balance out. Now can you see why, knowing the difference between sulfate and sulfite and thiosulfate, that is going to change the number of your elements, which is then going to change the value of your total mass of the compound, which is going to play an even bigger role later on. So if you have 1 mole of magnesium sulfate, you're going to have 1 mole of magnesium. You're going to have 1 mole of sulfur. You're going to have 4 moles of oxygen. So go ahead and work this one out. Alright, so hopefully you did well. So for magnesium, if you look in the periodic table, is 24.305 grams for every 1 mole. Sulfur is 32.066 grams for every 1 mole. Oxygen, I hear everyone say it, 15.9994 grams for every 1 mole. So for magnesium, moles will cancel out. I'll give you 24.305 grams of magnesium. Sulfur is 32.066 grams of sulfur. And for oxygen is 63.9976 grams of oxygen. And then find the mass of the whole thing, add everything together. You would have a total mass of 120.3686 grams, is equal to 1 mole of magnesium sulfate.
Number 6. What is the molar mass of magnesium sulfate heptahydrate? This is better known as Epsom salt.
This is magnesium sulfate heptahydrate. Now, magnesium, we just did this one here. Magnesium sulfate, magnesium again is Mg positive 2, sulfate is SO4 negative 2. But heptahydrate is a hydrated compound, which is a dot 7 H2O. Hepta means 7, hydrate means water. The common name for this is Epsom salt. So even though it has 7 water molecules for every 1 magnesium sulfate, this is still a solid. So the stuff that you might have at home for Epsom salts, that's this whole compound right here. So even though it's a dry solid, there are 7 water molecules attached to it. So we're going to find out what is the weight of this whole thing. And later on, we're going to be using this for a couple other things. So you'll see this kind of come up a little bit more in the future. So let's do this again. So if you have 1 mole of magnesium sulfate, you're going to have 1 mole of magnesium. You're going to have 1 mole of sulfur. For every 1 mole of magnesium sulfate, you're going to have 4 moles of oxygen. Now, when we get to the hydrate part, again, this is all one molecule. And it's kind of a molecule within a molecule. Is that you have 7 water molecules attached to this magnesium sulfate. So if I have 1 full group of this, I'm going to have a total of 14 hydrogens, 7 times 2. And for oxygen here, I have 7 times 1. I'm going to have 7 moles of oxygen. Now, you might be looking at this and it's like, well, wait a second. I have oxygen here, and I also have oxygen here. Can you add these two together? Yes, you can. But in this particular situation, I do not want you to doing that. Technically, yes, you can, but there's something else that we're going to be doing later on where I would like for you to keep these two separate. Okay? Now, if we weren't doing that, then yes, technically you could add the 4 and 7 together and come up with 11 moles of oxygen here. But in this case here, what I want you to do is find out what is the formula weight for magnesium sulfates, which you've actually have already done. And then what is the formula weight for water? And then what is the formula weight of the whole thing? Okay, so go ahead and work this one out. Alright, so hopefully you did well. So let's do this again. So magnesium was 24.305 grams for every 1 mole. Sulfur was 32.066 grams for every 1 mole. Oxygen, everyone together, 15.9994 grams for every 1 mole. Okay, and all these moles will cancel out. So when you do that Again here, we end up with 24.305 grams of magnesium, 32.066 grams of sulfur, and 63.9976 grams of oxygen. So the total mass here for magnesium sulfate was 120.3686 grams of magnesium sulfate. Okay, now let's go down to here for water. Water is 1.0079 grams for every 1 mole. Oxygen is 15.9994 grams for every 1 mole. Moles will cancel. So for hydrogen, you would have 14.1106 grams of hydrogen. For oxygen, you would have 111.9958 grams of oxygen. And so if I add these together here, we get a total mass of 126.1064 grams of water. Now, before we go a little bit further here, one thing I want to draw your attention to is that when you look at magnesium sulfate, if you were to make this anhydrous, in other words, if you were to take Epsom salt, heat it up gently, you can actually evaporate the water off of this. So just a little bit more than half of its total weight is actually made up of water, even though it's a solid. Isn't that amazing? I think that's kind of amazing. Alright, so now to find out the weight of the whole thing, to find the weight of this whole thing up here, what we're going to do is, the final thing is add up all the parts together. So when you add these two together, we end up getting a total mass of 246.475 grams is equal to 1 mole of magnesium sulfate heptahydrate. So this is our answer down here.
Number 7. What is the formula weight of ferrous chloride monohydrate?
Next one is if you have ferrous chloride monohydrates. So what I'm going to do is I'm just going to give you the formula. Ferrous is iron with a positive 2. Remember, ferric is positive 3, ferrous positive 2. Chloride is a monatomic ion, Cl negative 1. Positive 2 and negative 1, so you need 2 chlorides. Monohydrate, mono means 1, so you don't write 1s down. Hydrate is water, H2O. So, if you were to have 1 mole of ferrous chloride monohydrate, what is the formula weight of this whole thing? So solve this just like the previous one using the magnesium sulfate heptahydrate. Alright, so hopefully you did well. Let's go and work this one out. So 1 mole of iron would have 2 moles of chlorine. And then if you're looking at water, you're going to have 2 moles of hydrogen, and then 1 mole of oxygen. So to find the weight of the whole thing, actually we're first going to do ferrous chloride, and then we're also going to do monohydrate, and then the weight of the whole thing. So ferrous is 55.847 grams for every 1 mole. The chlorine is 35.453 grams for every 1 mole. And for hydrogen, hydrogen is 1.0079 grams for every 1 mole. And oxygen is 15.9994 grams for every 1 mole. Alright, moles will cancel, leaving you with grams. So for iron, you would have a mass of 55.847 grams of iron. For chlorine, it would be 70.906 grams of chlorine. For hydrogen, it would be 2.0158 grams of hydrogen. And for oxygen, it's 15.9994 grams of oxygen. Now, of just ferrous chloride, that would be a total mass of 126.753 grams for every is equal to, or grams for ferrous chloride, Cl2. For water, the total mass would be 18.0152 of water. To find the mass of the whole thing, you want to add everything together. You could also add all these together as well. But I think it's also kind of interesting to see how much of it is ferrous chloride and how much of it is also water. So in this case, the total mass will be 144.7682 is equal to 1 mole of ferrous chloride monohydrate. So hopefully you did well. If you have any questions, let me know. You can email me, and then we're going to be moving on, and we'll be using this information to solve for the upcoming parts. I'll talk to you later. Bye.